What is voltage clamp and why is it so important? Voltage clamp enables you to control the voltage of a neuron and to record the currents at different voltages. Why would you want to do that? Well, because we want to be able to study current and the opening and closing of ion channels in isolation from all the other parameters. Because what happens, of course, in a cell, if you remember, you've got voltage gated ion channels. And if you're trying to study these things, if you change the voltage, then that itself will change the way the ion channel behaves. Let me show you what I mean by that. So for example, let's say you wanted to look at the way currents across a membrane change at different voltages, and you want to go from, say, minus 70 to plus 50, and then you want to measure the current here in an ion channel. Well, naively, what you might do is you might say, well, here's my cell. I will record from it, and I will measure my voltage. Sorry, I will use this to control the voltage, and I'll use another electrode to measure the current. I start off at minus 70, and I find there's not much current. I gradually increase the voltage. I'm hoping to get some sort of linear relationship, but of course what happens is, once I get to the threshold, I'm just going to get an action potential. So what do I record for my voltage? This is exactly what voltage clamp is for. So the idea is that you control the voltage and then look at changes in current. How is it done? Well, it's done by a very simple trick using negative feedback. So what I do is I get my cell, and in this case I'm going to put in an electrode to measure the voltage. So I'm measuring the cell's voltage. Okay, it comes out, say, minus 70 millivolts, something like that. And I compare that to the voltage I want it to be at. And we're going to call that the command voltage. I don't like calling it voltage, it's potential really, but there we go. So I compare the two together. I find out what the error is. So let's say I actually wanted it to be minus 60. The error is minus 10. Now, I'm going to miss out some key steps here to make it nice and simple to start with. So what I now do is I do minus, so error times minus 1. So now I've got 10, and I feed that back into the cell. So now that's going to go up plus 10, and it'll bring me back to from minus 70 up to minus 60. That's really, really simplified. There's some things that are a bit wrong with this. First of all, what we inject here is not voltage but current. So it's not really that, but at least it's a positive current because we've times it by minus 1. And then the other thing we do is we don't just times it by minus 1, we actually times it by minus an enormous number. Let's say 1,000,000. Why are we doing that? Well, what that does, it means that the tiniest error will result in a huge current opposing that error. And you think, well, that's going to overshoot, surely. No, it's not, because provided it's quick enough, as soon as we start to inject this massive current, the error goes down, so this difference goes down, and so the injected current goes down. So this is negative feedback, and then all I've got to do now is to measure how much current I'm injecting, because that will be exactly equal to the amount of current crossing the membrane. So voltage clamp gives me two things. Oops, clamp. I correct that. Voltage clamp gives me two things. It gives me control of the voltage, and it gives me a measure of the transmembrane current. So it's the total amount of current crossing the membrane. And that's what voltage clamp is for. So typically what we would do is we wouldn't just hold it at one holding potential. That would be a fairly boring experiment. What you might do is you might start off with a step up for a few seconds and then back down to the command. So let's say this is minus 90. We're going to go up to minus 80. Then we'll do the same thing again, but this time we'll go slightly higher. Okay, so our first one to minus 80, we might have seen really not very much at all, just the passive membrane currents. Minus 70, just a little bit more perhaps. But then when we start to reach the threshold, what we notice is we then get this inward current, which then declines very quickly, and that's the sodium inward current. It's because sodium now is entering the cell, and then after a while that decays because of inactivation, and then we get a sustained outward current, which is because of potassium leaving the voltage gated potassium channels. And then what you would do is you would then plot the size of these currents at different voltages, and you find that as you get more and more positive, this one now starts to go the other way. And that's because the sodium channels are opening, but this is now so positive in potential, because you're now, say, plus 90, is now the voltage gradient is strong, pushing the sodium out, is stronger than the sodium coming in. So that's an example of how you would use voltage clamp to produce the sodium current plot, current against voltage.